scientific notation problems. Yes, next Wednesday, not today. It'd be a great little birthday gift. Be an excellent birthday gift. Colin, did you get here late today or something? They had you as absent earlier. You here? I guess she was excused. So if you disappeared, no one would ever know. No. But don't. First one, not scientific notation. Second one, take it out of scientific notation and then solve for the other two. Yes. As soon as we understand this, it's not much to this. Today's a very important day, and it's an awful day to miss. Yesterday's nothing compared to today. I'm 100% positive. Which one? Yesterday is nothing compared to, missing yesterday is nothing compared to missing today. A lot of important stuff today. If you understand this stuff that we're going to talk about in the next 2 days, that is one of 5 things that will make your life easier in chemistry. 1 of 5. The very first thing, we start today. The next thing I'll tell you about in a couple of days. And the next one I'll tell you in about 2 weeks. That's the plan. I might postpone it a day. Depends on how everything notes play out. Even if you weren't here, I pretty think you can figure it out. Yes?
Number 2, it says
Yeah, standard notation, ordinary notation. In other words, get it out of scientific notation. Yes. That's it. Yes. I missed. Okay, so let's call on some people. First one, put in scientific notation. Brantley, what'd you get? To the negative what? Yes. All right. Scientific notation, the decimal place just moved over 1. I mean, you're not just counting 1, 2, 3. Every time you move to the right, you are subtracting an exponent. So you're going -1, -2, -3. Look at -3. This should be between 1 and 10. Oakley, for number 2, we had to put this in ordinary notation, standard notation, however it's said. You just had to get it out of scientific notation. What did you get? It's a good year right there, 1982. All right. That's the year I was born. So I picked it. All right. Number 3, you had to divide scientific notation. Who'd like to help me with this one? Isa? Say again? To the... We'll finish it up. We had 9 times 10. What's the exponent? It's not 0 because it does not cancel out. And for the people who are not here, you can see what we're doing here. 9 times 10 to the third divided by, you can see it like that, you can see it like this. It means the same thing. All right, take care of your coefficients first. 9 divided by 1, it's 9. Now take care of your exponents. All right, to the third divided by 10 to the 8th, you actually do what? Subtract. So a lot of people do it in their head. It works, but this is what it looks like. Or let me do it right here. You have 10 to the third. Since I'm dividing, I'm subtracting 8. So in fact, what should I have? -5. Okay. I mean, if you always think of whatever you're dividing by or having the bottom as a negative, that might help. Right? So there we go. Number 4, multiplying or dividing. Well, multiplying and dividing. Who would like to help me out with this one? Michael. Oh, just the answer. That's it. Okay. Now, for those who were not here, let's do a little catch up here. You got two different notations. One's times 10 to the 6th, one's times 10 to the 5th. You need to have those the same. That's the only way you can multiply add or divide them. So we can change any one of them. We're going to change, let's just go with this one. This is what's given. We're going to add that with 3 times 10 to the 5th. We're going to make this 10 to the 6th. Well, to do that, you have to add 1. But if you add an exponent, you have to move that decimal that's right there one place to the left. And if you weren't here, then write this down. This is something that's going to be very helpful. I mean, we could figure it out without this, but this makes it a little easier, in my opinion. So now we try it again. We got 8.0 times 10 to the 6th, and now we have 0.3 times 10 to the 6th. Add that up. Okay, bring the exponent down. It remains the same. And then we got that answer. Right there. All right. We could have changed the first one. We could have made this to the 5th. Well, I guess let me show you since some people were not here. Let's see. If I went that route, if I want to make this 5, I have to subtract 1. If I subtract 1, I have to move that decimal one place to the right. So now I have 80 times 10 to the 5th, and I want to add that with 3 times 10 to the 5th. So now I'll get 83 times 10 to the 5th. That answer is different from this answer because scientific notation, it should be between 1 and 10. So to make this 1 and 10, you move that decimal right there. So now we have 8.3 hey, you moved it to the left, so I have to add an exponent. So that's same thing. The final answer must, if it's in scientific notation, it must be proper notation. Number 5, it's one of the easiest ones. Who'd like to help me out with this? Somebody different. Okay, Harper? You said to the ninth. Very good answer, but we're missing one thing. There. Yes, you did the math perfectly, but we need to make sure that's between 1 and 10. Move that decimal over, and then we add 1. 1.8 times 10 to the 10. Working with scientific notation. Yes? All right. Any questions about this? All right. Why did I make it a 10? Okay. Because it was 18, and I want it to be 1.8. It's hard for you to see right there. I'm sorry. It's 18, so I had to move that decimal over. That's right there. So if I move it over, if I move to the left, I'm adding an exponent. So that's why. I had to put in proper notation. Okie doke. Now, there are 5 things, like I said, in chemistry. We learn these, and we'll get them periodically throughout the year. It'll make your life easier in here. Make life a lot easier. The first thing is dimensional analysis. Basically, it's conversion. We're going to be using this all the way till May. So we're on page 6 of your notes, where it starts, dimensional analysis. There's a little on PowerPoint, but most of it is on the overhead and the board. Dimensional analysis. Let's talk about what it is. Dimensional analysis. Let it focus, and we're back. Okay. Dimensional analysis is a method of problem solving that focuses on units used to describe matter. Okay, units are important. So what we're going to do is we're just going to look like we're changing numbers, but we're not. We're really just changing units. The values are all equal. That makes any sense. By conversion, you're actually just converting units, changing those things. Often uses conversion factors. What is a conversion factor? This is what a conversion factor is. A conversion factor is a ratio. Ratio, like we're not going to say 5:1, like 5 to 1. We're going to be like a ratio is like miles per gallon. This divided by this. I'll explain. It's a ratio of equivalent values, like things that you talked about in algebra. X equals 2. X equals 5. 5x equals xy. Overall, all of those have an equal in it. It's an equivalence. Something equals something else. It's used to express the same number, but with different units, the same quantity. Example, you don't have to write this down. If you have a dozen roses, how many roses you got? 12. That's an equality. We can make this a ratio by doing this. 1 dozen over 12 roses. That is the same thing as that. It's the exact same thing. This is just an easier way of reading it. But this will mean the exact same. It means 1 dozen equals 12 roses. It also means 12 roses equal 1 dozen. Y'all see this? It's hard. I'll go up. Let me try to remember to do that. This is the same thing as this, which is the same thing as this. They all are saying the same thing. It's an equality. You want proof that this is the same thing as this? Hey, well, let's put everything on one side. If I divide both sides by 12 roses, this cancels out, right? All right, look what I'm left with. 1 dozen over 12 roses. Exact same thing. We're just manipulating it. But we can do the opposite. Right? If I divide this side by 1 dozen, that means that whatever I do on one side, I got to do the other. Divide that side by a dozen. That cancels out. Now I got 12 roses over 1 dozen. All right? This equality is the same as this equality, or the same as this equality. The only difference is we usually have this in our head. All right? We know things like this. Like 1 hour equals 60 minutes. Things like that. We know these things. Others we're going to learn. But we're going to use it this way in a dimensional analysis problem, which is just conversion. All the same thing. All right, first example. How many hours are there in 1 year? Every one of your conversion problems, it's going to give you one thing and ask for something else. Well, I give you something in parentheses, but ignore that. That's to help us solve it. But just looking at the problem, what does it give you? What value does it give you? What actually number? 1. 1 year. With every problem, write down the first thing that's given. With every conversion problem, which is 1 year. Okay? And I'm going to write this to the side. It gives us years, and we want to find hours. So this is what we're going to do. I need to start off with a conversion factor. You multiply by a conversion factor. Let's see. And it tells us in our notes, assume that this year has how many days? 365 days. Okay, so we know this. We want to get rid of this unit. So I will put it right there. How does that get rid of it? Yeah, it's going to cancel out in just a minute. All right. So anyway, we know 1 year equals this many days. So 1 year equals 365 days. The year will cancel out. Do we want days? No. Well, our final answer, we want years. All right. We don't know how many hours there are in a year, so we have to go step by step. Let's get rid of days. We know that in 1 day, you have what? 24. So I said 12? All right, it's okay. In 1 day, you got 24 hours. Day will cancel out with day. All right, we're looking for hours. That's our last unit. Hey, so we're at the units we want, so that's it for setting up the math problem. Because that's what we did here. We solved for it. You take your handy-dandy calculator, multiply everything in the top by everything in the bottom. So 1 times 360, ignore the 1 because it's going to be the same thing. 365 times 24, plug that in, and raise your hand when you get it. Ugly? There you go. And what's my units? Yes, days cancel out. See, down here, 1 times 1 over 1, that's not even important. With 1, just ignore that. So that's it. In 1 year, we have 8,760 hours. Now, something that's not in your notes. You don't have to write this down. But somebody says, hey, what if something's in the bottom? Well, let's do this. Let's say if I said, hey, we have 500 hours. And I want to go from hours to weeks. We can do that. All right? Well, first, like with any problem, we have to write down what's given, 500 hours. Start a conversion factor. Hours will go where? In the bottom. All right? And we don't know how many hours there are in the week. We can figure out that, but we know that there are 24 hours in what? One day. An hour will cancel out with hours. We don't want days, we want weeks. We know there are how many days in the week? There are 7 days in 1 week. A day will cancel out with a day. So whatever my final answer is, that's the unit right there. It's the only thing left. So what you do, you say 500 times 1 equals 500. Here, this is understood as a 1, so it's really not important. So you say 24 times 7, plug that in. 24 times 7, what is that? What was that? Just 168. Okay, there we go. That's not your final answer. Okay, divide. I think it's like 2.97. 96. Okay. 76. All right, so we'll just say 97. So almost 3 weeks. So if it's in the bottom, you multiply across. Hey, but something really nice about this? You do everything across the top, everything across the bottom, then you solve. 500, you could just say divided by 24, enter, divided by 7, enter. You're going to get this answer. When you multiply and divide, as long as you're doing the right function, it doesn't matter the order. But anyway, multiplied everything across the top, everything across the bottom, and then I divided, got an answer. Questions about that? This is dimensional analysis. This is conversion. We are going to start off talking about using metric conversions. Things we've used before. And these are them. Let me just run through the names. I'm going to write this on the overheads. It's not going to be on the PowerPoint. Let's go over the symbols for these names. Giga is a capital G. And I'll write them in just a second, so don't write anything down yet. Mega is a capital M. Kilo is a lowercase k. So you can have a gigameter. You can have a megameter. You can have a kilometer. You can have a hectometer. You can have a decameter. But right here, it's just meter. All right? Decimeter, centimeter, millimeter, micrometer, micrometer. Not actually right, but micrometer. Nanometer, angstrom, I'll talk about in a picometer. These are values. We can put anything with these. We can say gigasecond, megasecond, kilosecond. We can say gigagram, megagram, kilogram. We can say gigamole, megamole, kilomole. It can be anything. Let's use meter for right now. All right. Now, what I write is what you're going to get, is what you write out to the side. These are the conversion factors. Beside giga, 1 gigameter is equal to 1 billion meters. We're going to write one of these for each one. Because if we can figure this out, we can write it like a fraction. And you know what? Since that's a big number, let me also give it to you like this. 1 times 10 to the 9th meters. So if you gigabyte, you have a billion bytes. Right, but we're using metric conversion here. Beside mega, 1 capital M megameter means you have 1 million meters. Which is 1 times 10 to the 6 meters. Next is lowercase k m. 1 kilometer or kilometer That is, anybody want to guess? There we go. 1,000 meters, which is 1 times 10 to the third meters. If you have 1 hectometer, that's a lowercase h with m, that equals 100 meters. I'm not going to do a notation for that one. We're going to get smaller and smaller and smaller and smaller. These go in an order. Then we have 1 decameter. There's a couple different ways of saying that. Decameter is a DA. It looks like the word dam, or something like that, but decameter. So if you see DAS, that's a decaseconds. If you have a decameter, you have 10 meters. And then for the base, we're talking about meters. So 1 meter equals 1 meter. And since we're here, know that this can be anything. It can be a gram. It can be a mole. It can be liters. It can be meters. It can be seconds. It can be Kelvin. All right, it can be almost anything base unit wise. So that means up here I could be talking about a gigakelvin or gigaseconds. So don't think that M is the only time you'll ever see this. Carmen, I need eyes up here. I need your bag on the floor. Not a good time to lay down. All right. So that is your base units. We're still going to get smaller. And do not write this one down. I'll tell you what to write. 1 decimeter equals 1/10 of a meter. Don't write it yet. And right below that, 1 centimeter, right, is 100th of a meter. But you know what? I don't like decimals. So what I'm going to do is this. I'm not going to put it in scientific notation. I'm going to get rid of that decimal by moving 1 place to the right. All right? If this is an inequality, if I do it on this side, I have to do what? Got to do it on the other side. Move the decimal. So what I actually have is 10 decimeters equal 1 meter. Carmen, if you're not up here, this is really going to hurt you. I mean, I was trying to stress this earlier. So you need head up, eyes up, hand on a pen, because we are writing all this down. All right? Can't stress it enough. All right, so you know what? Write that one down. It gets rid of the decimals. I'm going to do the same thing to the other. All right, I'll move 2 places over. So 100 centimeters equals 1 meter. Because we're still getting smaller. Yeah, what I crossed over, don't write down. I'm just showing you what I did there. It's still getting smaller, though. Okay, next one is milli. So 1,000 millimeters equals 1 meter. Micro. This will be in notation. 1 times 10 to the 6. In other words, if you have 1,000,000 micrometers, which is kind of like a fancy U, it's a lowercase Greek symbol for mu. That's what it is. It's like a U with a little dash there. Equals 1 meter. A nano, 1 times 10 to the 9th, it's an N, nanometers. In other words, 1 billion nanometers equal 1 meter. Angstrom, that is 1 times 10 to the 10th. An angstrom is an A with a little circle on right touching the top of it. Meter equals 1 meter. And then pico is 1 times 10 to the 12th, it's a lowercase p, equals 1 meter. I put an angstrom or angstrom in parentheses because it's only found in biology. If you were talking about the size of a mitochondria or a protein, you will commonly see that symbol right there, or an angstrom, in biology. That's one we're really not going to use. The other ones, yes. But the centimeters, millimeters, decimeters, if you have a meter, you have 10 decimeters. 1 decimeter, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's right. So if I have a meter, which I have here, I should have 100 centimeters. Those are the small ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, up at 20, 30, 40, 50, 60, 99, 100. Yes. And if I wanted to count the millimeters, there's the real small ones. 1, 2, skip a few, 99, 100, 1,000. All right? Now, we had a question? Thought somebody had a hand up. Okay. So, these are important. These, we can write any of these as a ratio, like right here. We'll go with the 1,000 millimeters equal 1 meter. We can write it as this, or we can write it as this. How do we know which one to use? If we want to use this, how do we know which conversion factor to use in a problem? Well, it depends on what you want to get rid of. If I give you 5 meters and I want you to convert that to something else, you're going to use this one, because I'm going to say 5 meters and it's going to cancel out. But if I said 5 millimeters, convert this to something else, you're going to use this one, because 5 millimeters, the millimeters need to cancel out. All right, let's do some more. Does everybody have this? All right, this is utterly important. It's very important to have this, because we're going to be referring to it now for a long while. Okay, so we have our first problem, first example. Example 1. How many meters are there in 48 kilometers? First things first, write down what it gives you. 48 kilometers. The very first thing everybody should do with any type of word problem. Underline it if you need to, but if you're doing a problem, write it. Then start a conversion factor. That's the first 2 things you should do. Write the number given with the units. Don't leave off the units. I don't know what you're talking about, because when we're dealing with a lot of units, we can get very confused. Okay, write down what's given, conversion factor. What should I put in the bottom? Okay, yeah, 1 kilometer. Look at the top of the list. All right, well, we're looking for meters. Is kilometer related to a meter? Yes, because we saw that 1 kilometer is equal to how many? 1,000 meters. Kilometers will cancel out, and we're at the unit that we want. So you say 48 times 1,000. Don't even calculate for that. What is that? 48,000. Just like so. All right. I got 3 practice problems right below that. Let's see. I'm asking what conversion factor should be used to the following. Now, for A, B, and C, just do the conversion. Convert what's given to what it asks for.
It's right here. you wanted to put big G, little m, big M, little k, little m. So it's like a gigameter, megameter, kilometer, like you did right here. So a gram could be any of these. Instead of saying meter, imagine all those were grams. I mean, that could change. So, yeah. So, but right here, you kilogram and a gram, it's like saying a kilometer and a meter. And you wrote everything out instead of doing all the numbers. So I'm pretty sure you understand your writing. I'm only going to look at number B because that's the only one I know you worked out. But 1 gram equals 1,000. No. You didn't write these down up here.
All right. Remember, you need to show work for this, right? Because I'm going to be telling you to do that all year long. Don't just think you can plug in your computer and get an answer, because come Wednesday when it comes to a test, I need to see work. If I just see an answer, I don't care if it's right or what, you're going to get it wrong. No work, no credit. So, for A, the first thing you should do is write down what's given. 360 seconds. So, next thing is start a conversion factor. Just like I did, make a line and put a S underneath it, because I know I need those to cancel out. I want milliseconds. So looking at the conversion factor I just used, I know that, or let me show you how I wrote it, how you wrote it above. We see that 1 meter is equal to 1,000 millimeters, right? So we wrote down. So that means that 1 second is equal to 1,000 milliseconds. All right, the base units don't matter what they were. 1 second, 1,000 milliseconds. Seconds will cancel out. What math function am I using here? Multiplication. Right? And you should have got 360,000. What's your units? Milliseconds. Just like that. Show your work. And you should be copying down my examples, because these examples are the only thing you got when you are alone at night trying to figure this out the day before the test. For B, we have 4,800 grams. First thing, write it down. Start a conversion factor. Grams in the bottom. Kilograms up top. We know that 1 kilometer equals 1,000 meters. So that means 1 kilogram equals 1,000 grams. A lot of people do this. The big number doesn't always go on top. The big number doesn't always go on bottom. You have to look at the units. 1 goes with kilogram. 1 kilogram. 1,000 grams. 1,000 grams. You divide here, and what's my answer? Say again? 48? 4.0. Okay, that's it. Kilograms. Just like so. All right. If your work looks like this, it's gorgeous. All right. You probably got